Okay.
What are you watching? There's some video up and it looked like some guy in a sombrero looking at some other guy. Never mind. I don't see it.
This?
Let's watch the video. Is that Mythbusters?
No. Well, it could be. I don't know.
I know I was thinking about birds.
Okay. Oh yeah, quizzes. If y'all pass those up. Today we're starting a little walk through of electricity. It's specifically we're going to be starting to focus on electricity in transit. Okay, so in motion. Now we've talked about static charges. We've talked about the forces on static charges. And so today what we're going to say, okay, well now what happens if we take those charges and let them loose? Okay, so if we take the charges and let them loose, guys, what we get is called current. Okay, and current is the movement of charged particles. We're going to draw a lot of parallels today between motion, or kind of our first semester stuff, and electricity. And so, in terms of moving electrical charges, we have current and we have voltage, are two kind of keywords. Okay, voltage. Remember, it was kind of like the force, or the potential energy of the charges, and the more charge got separated, the more force there was, and so dead battery, all the charge had been depleted, and a charged up battery, we've separated those charges. And so, in terms of making kind of a parallel, let's think of like a water hose, okay? And if I have a water hose and I turn it up, okay, two things happen. One, more water comes out, right? And two, the water, if it was landing right there, it's going to be landing farther, right? Okay. The voltage is really kind of how far is it going. Okay, it's how fast are the particles moving, how much force is there on the particles. Okay, our current is going to be how quickly is it filling up a bucket. Okay, so really almost charges per second, a flow rate. If we're talking about in terms of an interstate, okay, our voltage would be kind of like the speed limit, and our current would be how many lanes are there. Okay, making sense?
I just like
Okay.
the definition makes sense.
Well, but I want to make sure we differentiate between voltage and current. Okay, voltage, the driving force, how hard, how much force there is, how much potential energy the particles have, energy per charge. Current, the number of charges. Okay, so in terms of the water hose, if I wanted to increase the current, I'd take the water hose out and make it bigger, and more water would come out. Instead of coming through the water hose, we just go straight into we take the fire hydrant and open it up. We've got some current now, right? It might not shoot out as far as when I have a little bitty thing. Those little attachments you put on the end of your hose, and it makes it shoot like 900 feet. That's kind of an exaggeration, but whatever.
I like the soak
Okay.
setting.
What now?
I like the soak setting. You just like.
Oh yeah. So high current, low voltage. Okay, so guys, when I have current, okay, when I have current, the actual particle movement is being made by what particle? The electron. Okay. So in current flow, the particle in motion is the electron. Okay. And we just said a second ago, guys, the movement of that electron is being caused by voltage. Okay, also known as a potential difference. Okay, so there's a potential difference that's driving the electrons forward. The more electrons move, the more current. Okay, and the more potential difference there is, the more voltage. Okay, so does a high voltage always mean a high current? Not always. Okay.
You said potential one.
I mean, with those shower heads, you can have multiple settings. You can put it on one setting, and it's just like it's spraying really hard. Okay, and it hurts. But but if you're doing like the face wash commercial, and you put your hands out and you collect some water, and you go like this, it takes forever to collect some water in there because there's really not that much water coming out. Okay, it's high pressure, high voltage. Okay, but not much current. Okay, so current though, guys, is going to be defined kind of awkwardly as the motion of positive charge and not negative charge, which is backwards from what we think it should be. In terms of circuit diagrams, I'm going to bring that back up in just 1 second. In terms of circuit diagrams, guys, if I have a battery with a positive terminal and a negative terminal, let's say I hook up a light bulb to that.
Probably changing my bulb.
Okay, I hook up a light bulb. That actual particle movement, okay, electrons would be going from the blank terminal to the blank terminal. What? Negative to positive, right? I mean, the electrons are on the negative terminal, so they're going to go from the negative to actual particle movement is in this direction. Electrons go that way. Oh. I refuse. All right. Okay, however, guys, when I'm drawing in current, we're going to define current flow as this direction. So that seems backwards. Okay, I mean, in terms of movement, there's not a particle moving in that direction, but there really is kind of something moving in that direction. We'll talk about that in a second. Making sense so far? Okay, so it's kind of backwards, but we just go with it. All right, so that seems backwards to us, guys. So current is technically the reverse of particle motion. A lot of people they say, oh, lightning moves from the ground up. Well, technically, current is from the ground up because it's the direction of positive motion, and the ground is positively charged. So that would technically be right, but we know that particles are moving down. So I think really of current, and instead of the movement of electron, I think of current as the movement of electron holes. Okay, and what I think, guys, is when an electron moves forward, it's going to kind of leave a void. Okay, and that void should be blank charge.
Neutral. Positive.
Positive, okay? It should be positively charged. If it leaves, if an electron leaves, it leaves a positive charge. So in terms of these, let's say these are all electron holes, and I'm going to fill in every other one with an electron, okay? So now the red is going to represent the electron, and the black will represent the electron hole. If I take one of those electrons and move it to the left, do you see how the holes kind of move to the right?
The hole?
Okay, now the hole doesn't move, but do you see how the sequence moves to the right a little bit? See, pay attention to this, this little red spot here. Okay, but we'll pay attention to this black spot.
Yeah.
Okay, watch the movement of this black spot. We're here, and now we're back one. Okay. So the electrons are moving this way, holes are moving this way.
So which one's stationary?
Huh?
Which one's stationary?
Well, the protons are stationary, but
Okay.
positive charge is moving in the other direction. Because of,
Electrons are leaving.
It's just lack of
Yeah.
negative charge.
yeah, so the lack of negative charge is moving.
Yeah.
Yeah. That makes sense? I don't know this for a fact, but I would guess that they probably defined the direction of current before they knew what an electron was. And it was one of those, oops, got that fixed. It's too late now. I guess we could start a trend now. We could say, forget it. Forget all we want. Uh-huh.
They wouldn't believe us. They would laugh at us for being
Our physics teacher in Mississippi told us that current was negative flow.
They say I have a million accents.
And now that's going to be for the entire world.
Yeah, well, all 4 people that have watched the YouTube videos, which I'm sure are y'all.
He got
Um,
I watched one of them twice.
So there's 3.
And I fell asleep the second time. I watched it the first time and then just listened to it the second time.
Is it just like play in your sleep kind of thing?
Yeah.
I
I've heard that it's just kind
it's
of
hard to do that.
different, like,
I
feels
tried to
that
do
you're breathing
it.
that way, so.
Okay, guys. Anytime I have current flowing, okay, current always flows through a circuit. Okay, and a circuit is just going to be a closed loop. Okay, in the same way that a racing circuit is a closed loop that cars run around. Okay, an electric circuit will be a closed loop through which electrons go around. Okay, so in a circuit, are any electrons introduced? No, they just move around. Okay, so if I have a battery hooked up to a light bulb, electrons are just moving. Okay, same thing with a generator. Okay, if I have a generator hooked up to something, just moving in a circle. Okay, and so every circuit has 2 things, guys. The first is a charge pump, and the second is a path for the charge. We're going to cover those in reverse order. The path for the charge, y'all know, guys, has to be a what? A conductor. Okay. So the path of the charge has to be a conductor. And the charge pump, take a guess. What do you think? It could be a capacitor, it could be a battery, it could be both. It could be a generator. Okay. Be a generator. Okay. So the charge pump, guys, is either batteries, generators, or capacitors. And those actually work. The battery and the capacitor work kind of similarly, and the generator is going to work just a little bit differently. Okay, a battery and a capacitor. Okay, essentially the battery and the capacitor. The example I like is our example with the bucket of water. Okay, I take a bucket, I fill it with water, I take it, I lift it up here, and maybe we have a little path, pour it, and it flows down the path, right? Okay, so I lift it, I give it potential, it flows down the path. Okay, that's the way a battery and a capacitor work. And how do I give it potential? Well, no, not the water, the electrons. How do I take the electrons from one side and add them to the other side, right? So that the electrons aren't over here. I've separated them, so that's how I build up potential. Okay, with a generator though, it's a little bit different. I think of a generator almost, instead of a hill. I mean, a generator does generate a potential difference, but I don't build up charge on the generator. Okay, a generator takes charge and pushes it. So I don't know of a good parallel other than in the same way that a car, the motor pushes the car forward. Okay, so the generator does that to electrons, or like a water pump. Okay, a water pump takes water and pushes it forward. Okay, so instead of a bucket lifting up here and then letting it go, the water pump's just shooting it up there. Okay. This is a generator right here, guys. I'm gonna pass this around. I want you to do 2 different things. We're gonna feel the difference between when you are moving electrons and when you're not moving electrons, because you can feel the movement of electrons. Okay, so when these are not connected, okay, that no electron should be moving. Okay, when you turn this, the only thing that you should feel will be just the resistance in here. Okay, so like friction and the gears and all that kind of stuff. Okay. However, what I want you to do, guys, is it's going to take two people. Turn it for a little bit. You know. It does that. It's fine. It's supposed to do that. Turn it for a little bit, and then get one person to take these two ends and touch them together. So I'm going to give you an example. So turn that for a little bit.
Wow. That's
it. So you feel the difference. And now you're pumping electrons. Now you're not. Okay. It's almost kind of like driving. You're driving uphill for a little while. Now you're driving downhill. Okay.
So you straight put your Honda in reverse.
I don't do that. Okay. So, and that won't shock you. It's very low.
They must have hard to turn.
Joe, over.
Mom said you break your back. You better run.
You can feel. I mean, you have to push those electrons.
Conscious, man. You gotta
Okay.
Can you make it work?
That. Leave it there for a second. Okay. Oh, by the way, I want to make a random comment. Have a good one. A generator to me is a lot like a fan. Okay, you take but
Alright, break it.
sorry, you take a fan, you plug it in, it turns the fan, and it takes air particles and moves them, right? Okay. But what happens if you take a fan and you put the air particles back toward the fan? It spins the fan, right? So you can take the fan and move the air particles, or you can take the air particles and spin the fan. Well, if you think, can y'all think of what essentially what a fan spinning is? Can you think of an example of us using a fan? A windmill, really? Okay. So I mean, a windmill and a generator are really. A windmill and a fan are really the same thing. So right here, okay, if we use this to, I'm good about it. We use that.
Are you gonna charge the battery?
No, we use this to almost kind of like a fan. Okay, I'm turning this and it's moving the electrons. What if I just move the electrons against it?
turn that fan.
Okay, then what we get is if I move the electrons against it, then it's just a
How
moment.
come I can't turn that?
But the electrons are moving at a constant rate there.
What happened to putting it I don't like that.
Be careful with it. It's okay.
Looks like you broke that fan.
Is it working?
Yes, it works.
I ain't even messing with it.
Yeah.
I probably should throw the battery and throw it back to you.
I need playing with it.
Yeah. I'm just bad at playing. That would have been a demonstration to put on the document camera, by the way. The one where you plug the thing into the battery and then it turned like a fan. It's okay, that's
You win some, you lose some.
That's what they give me absent.
Probably look for a ring or
That's what
something.
I'm gonna say.
Tim gotta go.
No, give a shout out to the people here. Do it.
Okay, so in most circuits, guys, we use that flow of electricity to do something. So, for example, with this, it's okay.
See, you just had
It's okay, it's only $10.
So, in the example of this one, Okay, we can, if right there, y'all were just allowing the current to flow. But if I take the current and interrupt it with something, for example, a light. Okay, then what we see is, that light bulb can use that movement of electricity in some fashion. Okay, so there we're just lighting up a
My
bulb.
brother has a flashlight that he uses for Boy Scouts, and he has to like pump it to get it to.
Mm-hmm.
Do you
So but he's charging a battery though.
So can
Okay, so-
you have to stimulate the human body?
Like, what do you mean?
like shocks?
I mean, no, like.
Like to make
Can
you?
you create a
like-
defibrillator?
No, it's not high enough voltage.
To charge it, like you press the gas. Like you know, if you're on a roller and like charge it, like get the battery fill up, and, like,
When you press the gas, it turns the alternator faster. If it turns the alternator faster, then it charges up the battery.
Mr. Lisenby.
Yeah.
So could you use that handheld generator? You probably could you use that handheld generator to charge up your capacitor that you made?
You could, but it's such low. I didn't make that capacitor low, but it's such low voltage that.
No, generator?
Yeah, that's very low voltage.
You can only use standard generators?
Well, that's 200,000 volts versus 6.
Wow.
So, guys, to use this electrical energy, we use the force behind the particles or the electrons to turn mechanical parts or to produce heat. Okay, in the same way that if I have air moving, we put something in the way, like a windmill. I have the air moving, I put the windmill in the way, and that turns the windmill. Okay? Well, in this example, okay, if I put the generator in the way of the moving charge, it turns the generator. Okay? Or I could take the windmill and I could turn it, and that would move air. Okay, so really the air and the electrons, you see the parallel there?
Yes.
Put something in the way of the electrons, and the electrons have to. It's not a physical object. It's not like there's some little boundaries in here that the electrons are pushing. It's not like that, okay? But there is. No, there's not like a little electron windmill in there. It's more complicated than that. Well, actually, it's so simple, and we'll talk about it later. It's more complicated than a windmill, but it's very simple.
So if you took another generator and then you connected it to the leads of that, and then you started moving it, it would move in the same direction or the other direction?
Okay, no. So if you're saying, well, it depends on how you have the wires connected. If you flip the wires.
So if you have the leads like positive, positive, negative, negative, then it would move in one direction. And
But
if you switch the leads,
This doesn't have a positive and a negative. I turn it one way as positive. I turn the other way as negative. So
it says input and output on there, right? So that can display. You see on the top. You spin it. You turn it one way for input. You turn it. The
Oh,
other
yeah.
way.
No, it's output and output.
What?
It tells you which way. If you turn it rotational direction of handle. If you turn it this way, then it makes positive, negative, and if you turn it this way, then it makes positive, negative. So which way you turn it depends on the positive and negative. Same way, if you turn the fan the other way to move the electrons this way, and if you turn it this way, air particles. You take a ceiling fan, turn it the other way, it shoots up. You go this way, it shoots down.
Can't you like switch it?
If you mess up.
No, you don't. No, don't mess up the wiring.
I'm saying like you can change the direction the fan spins.
Yeah, and typically, like in the winter, if you want to have circulation in the room, but you don't want it blowing on you, then
Wow,
you
I've never thought of that.
How do you do that?
There's a little
switch.
Yeah, because if you don't connect the leads correctly, then it just doesn't work.
Did he say daddy or dad?
Yeah, well, yeah.
And then all you have is a light.
But the light probably doesn't work either.
No, the light works.
It's two different hookups.
The
Yeah.
light works. It's just the fan part doesn't work, and we're too lazy to take the fan back out and switch the hang put it in right.
Okay. That's a little unnerving, but we can talk about that later. Anyway, guys, a circuit through which current does not flow is called an open circuit. So closed circuit, current is flowing. Open circuit, current's not flowing. And the very, very basic open circuit, okay, is essentially you take a closed circuit and you put an insulator in there somewhere. Okay, so for example here, paper, electricity, it can go through paper, but it doesn't go through paper too great. Okay. So here, I have it connected. Now, it's on there as well, but that would be an open circuit. Okay, it's not. There's no current flowing. Okay, so I have open circuit, closed circuit. Simple, right? And open circuits are typically caused by switches. And so we see examples of that in the wall. Okay, if I want the light to turn off, I turn the switch to the off position. It takes the current, and the current stops. Okay, it makes it into an open circuit.
So when you turn it off, there's an insulator somewhere in the whole circuit.
There is, and I'm going to teach you about that insulator right now. What now?
So you're really not saving electricity by turning off the light, you're just putting a piece of rubber in it and still wasting it.
Well, the electricity is
Oh yeah.
Okay. So this is
They don't know my name.
oh, that's zoomed in. This is a very basic circuit here, guys. And I'm going to just kind of walk you through how this works. I come from this terminal, the positive terminal of the battery, and it hooks to here. Okay, this, you see there's a little gap here. Okay. Ooh, I shouldn't have done that. There's a little gap here. Y'all see that little air gap?
Yeah.
Okay, and so I can take this little part and push it down, and when it connects that gap, okay, what we should see is that light turns on. Okay, so this is just a very basic switch. Okay, now the thing that the gap is connected to, okay, goes to this. Okay, this comes over to the light, and then the light goes back. Okay, so when this is connected, it's almost like this object not being here. Okay, so when it's up, there's a little air gap. An air gap is also a very good insulator. Okay, and when it's not touching, then it's an open circuit, closed circuit. What is this probably used for? Morse code. So SOS. Okay. Yeah, that's SOS.
That was SOS?
Yeah. Yeah, that's SOS.
Yeah, how do people sense Morse code?
I would be spelling out.
It's like you can do the SOS symbol, but you're gonna alert the sensor.
What now? What if you what now?
What if like you're stranded and you don't know what SOS is and
Start screaming.
Well, okay, guys, if y'all don't know what SOS is, let me just go ahead and tell you. Okay, just want to let you know what the universal distress signal is. Okay, okay, but there's two universal distress signals you need to know. Okay, the first one, a flag being upside down. Okay, that's a universal distress signal. If a flag is hung upside down, that's a universal distress signal. Yeah. So that flag, if it was upside down, that would be a universal signal. So if we hung the flag upside down outside, people would know something's probably wrong in the school. Okay, obviously we have cell phones now, so they would probably not pay attention to that. They would think stupid high school students hung their flag upside down. But then the other one is SOS, and SOS is three short signals. So do, followed by three long signals, do, and then three short signals. Okay, so SOS is da 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 da. Yeah. Anyway.
So is that how the light switch works when it's on? There's like a
Yes. Okay. So, all right, guys. That's not. All right. So, basic switch. Essentially, you basically just take the two terminals and disconnect them. Okay. So that essentially all it does is it's connected and then it's just disconnected. The most basic switch, remove a wire from a battery. And so this is kind of our open circuit signal. Where if you flip the light switch up, we're just taking something and we're just disconnecting it. Okay, there we're letting the insulator be air. Notice how sometimes if you take the light switch and you just kind of, don't turn it all the way on, turn it just a little bit on, the lights flicker a little bit, and it makes a hissing sound, you wonder if you're about to burn the house down. You know what I'm talking about? Okay.
I'm pretty sure I messed up my light switch in the bathroom.
I'm not suggesting you do that, that's the reason I'm not demonstrating. Typically I demonstrate things, if it's right over there. But I'd like to not burn down the school. And then a closed circuit would be this, that symbol there. But yeah, when you have it in that kind of awkward zipping, okay, I mean, it's close enough now to where the air is being ionized, a little bit of charge is flowing through, okay, but it's not completely connected. Okay, when air gets ionized and charge flow through, it gets really hot, and that's the reason why it typically can cause fires. No.
Is that how the light bulbs that you can dim and stuff work? Is it just you close the circuit more and more than the air ionizes?
No.
Is that what parents do?
I think it was a cartoon.
It's not just because it's annoying, I think.
Yeah, I do think that's probably just annoying.
Are you going to explain how the dimming light bulbs work?
Does that have to do with voltage and current?
It has to do with resistance, and we haven't gotten there yet.
Resistance? Okay.
It's variable resistance.
Okay.
So actually, those light bulbs those circuits are kind of interesting because you would think, oh, it's the light is dimmer, it must be using less electricity.
No, it's just lower.
It's just now instead of using electricity in the light, you're using it in your wall. So I mean, it's just the same amount of electricity. You're just wasting perfectly good electricity. Yeah, just get a dimmer bulb if you want a dimmer bulb. Don't use a dimmer
Yeah,
switch.
just change out the bulb every single time you want to dim the lights.
There you go.
I know I'm just
Alright, guys.
every single light bulb every single one.
Grab a partner. Talk it out.
And the current is not flowing more.
That's the whole reason.
Because the wire.
Yeah.
Connection to positives and negatives.
Yeah. Well, no. Yeah, we're saying that is not typically what happens. But, No. And if you have a light bulb on and the glass busts, it's going to break. It's not.
Yeah, if you.
Oh, yeah.
Unless the current is the exact same as the voltage, then you increase the voltage. Yeah. If the current matches What do you?
I just enjoy hearing y'all
You just
banter.
enjoy watching students suffer during these talk it out.
Okay, let's talk.
Alright, let's talk as a group, guys. What causes the lights to turn on and off when you flip a switch in the wall?
Open and closed circuit.
It's an open and closed circuit. Okay, when it's off, it's an open circuit, so no current is flowing, and obviously when it's on, it's a closed circuit. You have a light bulb plugged in and turned on, it busts. Okay, so we're saying the glass busts, and so sometimes they say get a potato, and a potato can kind of help you get those out. And I've tried it; it doesn't work. But does current continue to flow through the light bulb?
Yes.
No.
But it's an open circuit.
Why
It's
not?
the actual wire inside of it breaks.
Yeah, I mean because if the light bulb busts and it's on, the filament is going to bust too. Okay, so you don't have a path for that charge to go through anymore, and so it's going to stop. Okay, is it safe to touch?
Yes. I touched one before and I was hurt.
Let's. No. No, let's.
No, he pulled out a piece of paper and a pen.
No, let's work it out. All right, you have a light bulb. Okay, it busts, and so now you have. I should have done that. Pretend like that's not there. Okay.
Typhoon.
Wait.
All right. As soon as that busts, guys, this filament's going to burn. Okay, so you'll have a little bit over here and a little bit over here. Okay, so the current's not flowing through there anymore. However, if you put your finger on there, there's a path for the current now. Guess what the path is? Your finger. Okay, so you would need to touch both sides of it. If you just touch one side, it wouldn't do anything.
What if you touch one side
Yes.
with your finger and the other side?
Then it would go through your body. Okay, but one little comment, guys, and this is kind of nitpicking, but if you put your finger on there like that, your finger is not going to be the only thing that gets damaged. Okay, because some of that electricity is going to want to go to ground. And how does it go to ground? Yeah, through you. So through your organs and through your legs. And what happens if an electrical signal goes through your body? No, with your muscles. Your muscles tense up. Okay, so if you're touching it, yeah, you're gonna be touching it until it stops. Okay, so yes, then we'll talk about that. Yeah, there is some protection in the wall, but now I have shocked myself more times than is necessary to count. Yeah, not on purpose,
There's a dude on YouTube who he puts leads on his tongue and then sees how much how high a voltage he can handle.
Yeah, no, that's stupid. You never test out electricity on yourself because then you can't turn it off.
And he does and he does I think it's actually kind of cool because he zooms in the camera on his mouth and you can see his tongue whenever he has it on high voltage.
Have y'all ever heard the story of the guy who decided he wanted to test the taser out on himself? I don't know if it's true or not, but according to the story, once you touch yourself, and it's not true because a taser does and it tick 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 tick. I mean, it's not a straight signal. But according to the story, 5 minutes or 4 minutes later, he finds himself on the floor and the room's destroyed because, and the cat's perched.
You know that whenever you buy a taser, they have to use it on you.
Yeah, that's not true. I don't.
My friend bought a taser and they had to tase him.
I have a friend that has a taser and he didn't have to do that. Yeah. I think there must be a taser salesman around here that has a really good sense of humor.
Maybe my friend just was like, all right, yeah, I'm gonna tase you, sir. Like, what?
Yeah.
And then he's like passing on the floor, and they just put the taser in his front pocket.
Guys, last one. If you increase the voltage on a circuit, listen up. If you increase the voltage on a circuit, what do you speculate will happen to the current? It's going to increase. Okay. I mean, if you have a water hose and it's spewing out farther, I mean, it's going to be more water too.
Okay,
So,
what did you mean earlier when high voltage doesn't necessarily mean high current?
Yeah, because like I was thinking about it like in terms of curves.
think of it as there is the current and voltage relationship is always aligned. And so, I mean, if I was going to graph current on one and voltage on the other, it's always aligned. Okay, but yes, but the slope of that line is not always the same. Okay, so I might have that. I mean, that's very high voltage, not so high current. Okay, I mean it's always a linear relationship, but okay, and what is what the slope of that line is going to be the resistance. We haven't talked about that yet, but that's what we're going to see there.
So whenever you like, what do most